Good. Good afternoon, everyone. Welcome to Wuzhen. My name is Matthijs van Spronsen. I'm a beamline scientist working for Diamond Light Source. There I run the ambient pressure, XPS, and X-ray absorption spectroscopy beamline. And I'll be chairing this session that I organized together with James Whitten from University of Massachusetts Lowell and Emile Haye from University of Nemours in Belgium. The program is as follows. Jim will start the workshop with a presentation about instrumentation, about the hardware. Then I'll follow with some fundamentals of XPS and where you can get into problems. I'll show some examples of not so great XPS peak fitting in literature, and then I hopefully can convince you to do it better. And then Emile will continue talking about death profiling in XPS, which is a very useful technique. And hopefully we'll leave 30 odd minutes at the end for questions, or if you have some problems of your own, some fitting problems you want to discuss, there should be time for that. So with that, I would like to give the floor to Jim.
Thank you. So thank you very much. My name is James Whitten from the University of Massachusetts Lowell, and since this is a workshop, I think it's important that this not just be a lecture. That if you don't understand something, please, at least as far as my part is concerned, feel free to interrupt. It's not rude. So we want to this to be a learning experience. So what I'm going to start with is sort of an overview of the instrument, of basically the basics of XPS and the instrumentation that's used. And so hopefully this is working.
Go down. The other button.
Oh, down. Oh, there you go. All right, so this is a picture of one of the instruments in my laboratory. We actually are fortunate to have 3 working photoelectron spectrometers. And so this one is the easy one to use. Then we have some that are more advanced. This is the one we use for routine analysis. And let me just kind of give you an overview here of what we're looking at. So over here, there are a couple of X-ray sources. You can't see them very well in this picture. I'm going to talk about how those work. There is an analyzer, a concentric hemispherical analyzer here. There is a flood gun for charge neutralization. There are actually, in this particular machine, 2 chambers. There's a small introduction chamber that's turbomolecular pumped. And the main chamber is also turbo pumped with an auxiliary ion pump. And I'll tell you in a few minutes why vacuum is important for photoelectron spectroscopy. So as you all know, these kinds of machines are pretty expensive. They're $500,000 and up. So it's important that you at least understand how these machines work, so that you, for one thing, don't damage them, and also that you use them correctly. So photoelectron spectrometers have become easier to use as time has gone on, as the decades have passed. They've also become easier to misuse. And so hopefully this workshop, the 3 of us, will be able to give you some advice there. We have some people that I see are experts here in the field. If they see anything they'd like to add at the end, I think that would be awesome. So let's keep going here. So first of all, what is XPS? X-ray photoelectron spectroscopy. It has an older name that you may have heard called ESCA. And I've actually heard, it is amazing. Years ago, somebody said, "Oh, you have ESCA and you have XPS." I said, "No, they're the same thing." So electron spectroscopy for chemical analysis is the acronym ESCA, but it's more or less becoming an obsolete term at this point. So how does XPS work? So X-rays shine on a sample. Usually it's a solid sample. And they eject electrons from core. We're going to be interested mainly in core electrons, ones that are close to the nucleus. And those electrons then are excited when they are excited with more energy than the vacuum level of the sample, they can escape and be detected. And so, because of conservation of energy, the X-rays have a certain amount of photon energy, designated here as h nu. And so if you look at an energy level diagram like this, we actually need to look at this side, because what actually happens when you put a sample in electrical contact with a spectrometer, something called the Fermi level, maybe some of you know that, they become equilibrated. And so there is a difference between the work function of the sample and the spectrometer. And so this is the part that actually matters. And so when you look at the details of this energy level diagram, the binding energy that you measure, that's usually what people report in the literature. The binding energy is the photon energy minus the kinetic energy that's measured minus the spectrometer's work function, and they can be related back to the sample's work function. What is work function? The smallest energy needed to remove an electron from a solid. Okay, so what are the advantages of XPS? The advantage of XPS, and it has some disadvantages, is really its surface sensitivity. It's one of the few techniques that can actually just see the very top level of a sample, the top layers of a sample. Typically, we're talking about 50 to 100 angstroms as sort of the analysis depth. Now, it has some disadvantages also. In general, it's pretty low in sensitivity, and in general, it's a low energy resolution technique. Now, I'm going to be talking about laboratory photoelectron spectrometers. There are also photoelectron spectrometers used at a synchrotron, and some of these disadvantages can be minimized when you do that. But we're talking here about the kind of XPS that you would probably have access to at your university or institution. So there's something called an inelastic mean free path curve. And so in general, to a first approximation, if you look at the inelastic mean free, let's say the escape depth here, the mean free path, lambda, that's mean free path, versus kinetic energy of the ejected electrons. The reason that XPS is so surface sensitive is that the ejected electrons, when you typically use the kind of X-rays that are used, X-rays are around 1,000 electron volts, 1,200, 1,400 electron volts that are typically used by analysts this day. It turns out you're near the minimum of this inelastic mean free path curve. And that's what gives you this extreme sensitivity. And so if you're looking here, around 10 monolayer, we're going to see in a few minutes that, you see basically several times, 3 times lambda typically in an XPS experiment. Okay, a surface sensitive technique, not necessarily easy to use, but certainly easier than it once was. Okay, here's an example of an XPS spectrum. This is a piece of clean gold foil, a piece of gold foil that was cleaned by sputtering with argon ions. And you see a pretty nice spectrum here. These are all the gold features. Here's the electron configuration. You can see the beautiful, clean designation of all these orbitals, these core electrons. And then the valence electrons are all piled up in this little part here. You can analyze, you can run that region, and some people are very interested in that. But in general, because these will all be run together, there's not a huge, usually there's not a lot of information in this part, but there can be for some experiments in semiconductors these days. People are interested in that. That's kind of another story that we could go into. But basically, it's pretty easy to get a spectrum like this. Notice there's no carbon and no oxygen. That's because this sample has been cleaned by ion bombardment. If you were to take a piece of gold and just put it in the machine, you would actually see contamination. So this is an example of the kind of spectrum you get. In this case, magnesium K-alpha X-rays were used, and those have an energy of around 1,200 electron volts. All right, so why do people want to run XPS? So the reason people want to run it, again, this extreme sensitivity to the surface we have, but you can notice that you can tell a lot about the molecules that are on the surface or the nature of the surface. So for example, if you just have aliphatic chains or what's called adventitious carbon, that's usually the kind of contamination that might be on a sample. Usually the carbon 1s peak is at around 285.0 volts. It's, you know, a range of values are often reported in the literature. If you took, for example, some polypropylene, a very common polymer, the commonly accepted carbon 1s value is 285. Now, unfortunately, samples will sometimes charge, and I'm going to talk about that in a few minutes. And so these values may actually appear, unless you are doing something about that charging, at different values, and you need to correct that. What causes charging? When X-rays impinge on the sample, they eject photoelectrons. That causes positive charge to build up, and those electrons that escape after that positive charge is equilibrated are shifted to apparent higher binding energies because of the attraction of those electrons to those positive charges. But the key thing about this table is you notice that there are some really nice energy differences depending on the functional group of the carbon. So if you have aliphatic hydrocarbon, you know, aliphatic carbons or hydrocarbons around 285. If you have a carbonyl, 288. You can see if you start putting fluorines on there, fluorines are very electronegative, we begin to see values around 292 or 293. So the carbon 1s is very sensitive to chemical shifts. Unfortunately, not all of the core levels are that sensitive. And so, for example, if you look at the oxygen 1s, you notice here you do see changes, but you don't see as dramatic a change. What this is going to mean ultimately is one is going to often have to peak fit. And that's one of the things that my colleagues are going to talk about that's important in order to extract the most information from X-ray photoelectron spectroscopy. Just to give you an example of, you know, what could I use XPS for? Here's some very old paper from my group, just to give you an application here, where we were interested in these old days in organic light-emitting diodes. That was the rage back in 2003. And how do you make an organic light-emitting diode? You take a piece of indium tin oxide, you put, for example, semiconducting polymer. We were interested in this one we nicknamed Purette. Notice that it has a urethane side chain here with some carbonyl groups, and then you put some aluminum, for example, on top. And it turns out that the interface between that aluminum and that polymer is real important for how these things function. And notice you can use XPS, in this case the aluminum 2P core level. What you can see, this is from the literature, aluminum oxide, the aluminum 2P core level, has a higher binding energy than aluminum metal. And what we see at the interface between this polymer here and the aluminum, you have aluminum oxide. However, as you continue to build up aluminum, the aluminum was being deposited in ultra-high vacuum, you transition to metallic aluminum. This is kind of one of the things XPS is really great at, studying the interface. Okay, what are the major components of a laboratory photoelectron spectrometer? So first of all, we have an X-ray source. Then we're going to have a sample stage, transfer lens, an electron energy analyzer, and then detector and obviously computer. Now, why do we need ultra-high vacuum? So, you know, all the surface scientists are all proud of you go into their lab and they always, the first thing you do is you look at your ion gauge. And because we care about that, and so why? Why do we care? 3 reasons. First of all, there are high voltages in that ultra-high vacuum chamber. The X-ray source, there's an anode, which I'm going to show you in a few minutes, and there's a filament. There's a high voltage difference between them. If you had a high pressure, you would have arcing. So also there are other things like ion guns, electron guns, and all of these are using high voltage, which would arc if the pressure is too high. The other thing is, if there were gas around, the electrons that are escaping from the sample would collide with the gas molecules and get scattered and never make it to the detector. And then in many cases, we want to keep the surface free of contamination. Otherwise there would be water all over it from when it was introduced. All right, the X-ray source. There are two types commonly used. There's a twin, what we call a twin or a double anode, and there's a monochromatic source. The twin almost always has an aluminum and a magnesium anode. Those are the ones everybody uses. You can get other sources, but those are the common ones. What is the difference? Well, you basically have a piece of magnesium on one side, a piece of aluminum on another, and you have two filaments. It's very easy to make electrons. You put about 15,000 volts on the anode, and then depending on which filament you pass electricity through, if it's on this side or that side, you bombard a different part of that anode. You have to cool the anode with water because there's a lot of power. And so water is typically flowing through this X-ray source. So here what happens, the X-rays are emitted. Typically there's a piece of aluminum foil, thin, very thin, much thinner than you buy at the grocery store. That aluminum foil is there to block something called brimstollen, which is basically stray radiation, and that would cause artifacts in the spectrum. Now, a monochromatic source, which is very common these days, is hard, it used to be really hard to use, not so much anymore. Here what happens is you basically have a similar thing. Usually it's aluminum anode, and those X-rays bounce off a crystal, and then they are, by Bragg reflection, they hit the sample. One of the advantages, there are two advantages of a monochromatic X-ray source over a twin. The first is you get a narrower band of radiation. So for example, here is the case of aluminum K-alpha radiation. The solid curve is what you would get if you were using a twin with no Bragg diffraction here to make it more monochromatic. With Bragg diffraction, you only get a much narrower range of energy, so you go from about 0.8 full width half maximum down to 0.2. The other thing is, with a monochromatic source, you can actually get small spot sizes of X-rays, and that can allow you to look at smaller samples. Okay, now what about putting the sample? What's the second part? The sample has to be there, the X-rays hit the sample. Now in the old days, and that old day means 20 years ago or something, this was common. There was a carousel, and you would put samples, you can see here, one on a stub. We still, by the way, use these sometimes, depends which machine. There are some advantages to these, but these are they're harder to do, they're harder to use. You have to actually, in the machine, pick the sample up and move it. And if somebody comes in and says, hey, Dr. Whitten, I've dropped several because of that. And then you can't get them out until you break vacuum. So these have the disadvantage that you can actually drop the sample, and they're harder to prepare and so forth. These are typical modern stages. So here you actually transfer this hole. Here you move the carousel in and out of the analysis chamber. So typically there are two chambers, preparation chamber, or could be more. And you pick that sample up with a wobble stick and move it. Here what happens, you put all the samples on a stage, and then you transfer this into the machine, and you can run whichever one. You could actually load this with many more than this. You can also have certain sample stages that are heatable, or they can be rotated for angle resolved XPS. Now, these days, these machines are computer controlled. And so these days, again, instead of the old days, what happens is you tell the computer, we don't usually do this in research, but if you're at a company, you might set up, 5 or 6 samples, and program the computer, the stage, to run them while you're at home watching television or doing whatever you're doing, because the computer can control the position of the sample stage in the machine. Okay, I need to talk a little bit about something called Auger peaks. So Auger can be done with an electron gun. Separately, it's a technique that has its own merits and advantages. But there also can be Auger peaks in your X-ray XPS spectrum. And so what is Auger, first of all? So first, let's take a look at this drawing I have here. So the first one we don't care about today. That's a technique called ultraviolet photoelectron spectroscopy, UPS. I won't go into that, but if you're interested in that, I have written a paper recently that tells, it's a user guide to that technique. Ask me and I'll be happy to share that as open access journal. Here, XPS, this is a similar drawing to what I showed earlier. Photons hit, they knock out core electrons, and then you measure the kinetic energy of those core electrons, which is related to their binding energy, which is related to the chemistry on the surface. Auger electron is something else. All right, the X-rays come in, they knock out an electron at a higher lying energy level. Then the atom redistributes the energy and knocks out another electron. Now the importance of the Auger electron is that that electron that is ejected by the Auger process, its kinetic energy does not depend on what wavelength or energy of X-rays you're using. And so when the computer takes the kinetic energy and translates it to binding energy, because these are not changing kinetic energy, if you go and you take two different anodes, so for example, this is an aluminum anode, a magnesium anode, this was run in a twin machine, what you will see is the photoelectron peaks will shift, but the Auger peaks will not shift, and the Auger peaks will. And so here you see an example where the photoelectron peaks have stayed at the same energy and the Auger peaks have shifted. This is very important because you run a sample, and if you try to identify something, you could have Auger peaks in there. There can also be other kinds of artifacts like ghosts and satellites, which I'm not going into. I don't know for sure my colleagues will or not, but there's certainly a lot of literature on that. Okay, how does the analyzer work? So almost all the machines that are sold these days are using something called a concentric hemispherical analyzer, also known as a CHA. These also have been known as sector analyzers, sector hemispherical analyzers, SHA. They have a few different names. It's important that you know how these work. Look, if the machine's working perfectly, you don't need to know anything. The problem is these machines will break down. And when they break down, they either stop working or you get nonsensical or crazy spectra. All right, this CHA, let's talk a little bit about it here. So first of all, there's something called a transfer lens. We sometimes call it a high voltage lens. The sample's down here. This is usually several inches, or if you want, multiple centimeters away from the sample. And the transfer lens has several functions. The first thing is it allows the sample to be further spatially away from the analyzer. It also allows you to accept electrons from a wider angle, which means more signal. The other thing that it does, and this is very important, is it pre-retards the electrons before they enter the analyzer. So actually what happens typically in what's called fixed analyzer transmission mode, or FAT mode, or constant analyzer energy mode, is that this lens actually takes the electron and slows it down before it enters the analyzer. So a concentric hemispherical analyzer, two spheres. There's a sphere here, there's a sphere here. That's why this thing looks like a dome, if you remember the first time I showed you. So the inner sphere is always more positive in voltage than the outer. That causes the electron to take the one that successfully makes it to the detector, to take a trajectory like it is a hemisphere itself. And so at the detector then, only photoelectrons with a certain pass energy will arrive successfully at the detector. Now these voltages are not necessarily positive, it's just that the inner is, they could both be negative, the outer and inner, but the inner is more positive. So let's see, for example, this is from this book here. If, for example, we had 100 EV retardation, that means it's slowing it down 100. If you came with an electron that had less than 100 EV, it won't enter the analyzer. On the other hand, if you came with 150 electron volt photoelectron, it would be retarded by 100, and then it would have an energy of 50 when it entered the analyzer, and it would make it to the detector. On the other hand, if you had 170 EV electron, it's retarded by 100. A 70 EV electron will not successfully pass. So this is what's doing the analysis. And you know, it takes my students, you know, and I remember the first time, quite a while to understand how these things work. Now, what's the importance of this pass energy? The larger the pass energy, the poorer the energy resolution. And so here's, you know, an example of that. And so 20 electron volt pass energy, 50, 100, 150. You can see the peaks are getting wider as the pass energy goes up. So if you are writing scientific publications, I really encourage you to report the pass energy, as well as things like the X-ray source energy, because it does affect the quality and the appearance of the spectrum. All right, now, this is not common in some machines. We do have in my lab an ability to do this, what's called parallel imaging. Let's say you want to map the sample. You know, honestly, it's time consuming and there aren't always applications, but sometimes it's useful. Let's say you would like to know where, I don't know, the fluorine is on a surface. There are two ways you could do that. One is you could just run in the way I showed you, and you could have the computer move the sample stage tediously. The computer knows the sample. It would make a map of all the different elements. There's another way, a faster way, has its pluses and minuses, called parallel imaging. So if you make some modifications to the CHA, and then it becomes known more commonly as a spherical mirror analyzer, one of those modifications needs to be a baffle. It turns out you can use the same analyzer, machines are sold, and you need a more sophisticated lens here. And so what happens is actually you just, this thing with a special detector that can get an image of the photoelectron, basically measures you get a map in some ways a quicker map. So there is a way to image with XPS, you know, the elements on a surface. All right, detectors, typically what people use are known as spiraltrons or channeltrons. And so usually modern machines use several detectors, and they'll have an array. Could be, you know, one of our machines had 3, one has 5. And so what's happening there is that at the exit of the concentric hemispherical analyzer, you have these detectors, and slightly different, you know, even though we're passing 50 EV, it doesn't just pass 50.000 EV. It might pass, you know, 50.5 and 49.5. And depending on where these detectors are situated, it will detect, it basically gives you more signal. But you have to have the machine calibrated correctly. Usually the manufacturer does that for you. Sometimes things can go wrong. Whenever you're running a detector like this, you don't want to over voltage it. So you always want to be at just where it plateaus, otherwise you'll reduce the life of the detector. So these again are called channeltrons. There's also something called microchannel plate detectors. I don't have a picture of one of those here. Angle resolved XPS. Let's say you would like to know, you know, do some depth profiling. There are a couple of ways to do depth profiling. One of my colleagues is going to talk about sputtering to do that, ion bombardment, where you remove material and do XPS as a function of depth. You can also do a more limited experiment, but not as destructive, so pluses and minuses, where you tilt the sample. And by tilting the sample, you can actually go from seeing perhaps 50 to 100 angstroms deep to much closer to the surface. And so this is where with a modern machine, typically you have, again, there could be computer control if you wish, or you can do things manually. The idea here comes down to this equation. And so if you are at a 0-degree takeoff angle, and by the way, some textbooks will, instead of 0 degrees, call that 90 degrees, so be careful. This depends on the nomenclature. But long story short, if you go from the electrons escaping perpendicular into the detector to at a more, I don't know, a oblique angle, I guess maybe that's the word, you begin to see, instead of, for example, I don't know, 50 to 100 angstroms, you can go down to sort of 20 angstroms by a tilt of the sample. So what that allows you to do is be more surface sensitive. It comes at a cost. You give up signal. All right, I am not an expert at near ambient XPS, but it's a growing topic, and I'll tell you a little bit about it because we said we would, and it's important. So take that $500,000 to $1 million machine and now multiply it by 5 or something, or 3 to 5, and you can get yourself a near ambient XPS. It allows you to run samples at much higher pressures. And so how does that happen? Because I told you why you got to have ultra high vacuum earlier. Well, what happens is massive differential pumping. And so essentially you have to pump all kinds of, you know, there's pumping. This gives you an idea. Basically, between the sample and where the photoelectrons get into the analyzer. And so why is it important that these days there's a lot of, this is also, by the way, called operando XPS. And so things that aren't not vacuum compatible. Maybe you would like to run a biological sample. Well, if you dry it out, you know, it's certainly changing the nature of a cell or membrane or whatever. Catalysis, certainly important. You know, all kinds of food, chemistry, and here's some of the examples right here, paper science, etc. So here you can typically achieve atmosphere, sample can be at a pressure of around 0.05 atmosphere. Okay, basic steps. I'm nearing the end of my presentation. I've come to the most important part, the basic steps in running XPS. First thing you need to do is ask yourself, is XPS really the correct technique to use? You know, it's terrible to just have a technique and be looking for something to do with it. All right, if you need to be surface sensitive, then yes, it could be the right ones. Do remember, the detection limit of XPS is roughly approximately 1 atomic percent. So if you only, I've had so many people come to me over the years, can you run XPS? What's your concentration? It's parts per million. I said, you're not going to see anything in parts per, unless it surface segregates. The other thing to keep in mind is it's low energy resolution compared to something like IR, or nuclear magnetic resonance. It also has limited spatial resolution. So is it the right technique? And when we're doing angle resolved XPS, we mentioned that a little bit earlier, you know, powders, I've seen some literature where people are doing and they're getting data, but it doesn't make sense. If you got to think, if you have a powder and the particles are, you know, angle resolved XPS really only meaningful when you have a very flat surface, for example, a single crystal. So be careful also with angle. Then, if you want to do, that's where the depth profiling with ion beam may be more useful. All right, is it the right technique? Have I prepared the samples properly? So here we go. You need to know a little bit about your sample. If it's a conducting sample, it's best to make electrical contact with the sample stage or the stub so that the Fermi level of the sample is indeed equilibrated with the Fermi level of the spectrometer. Now, if it's insulating, it might not be good to try to make electrical contact, because if you do, because charge will build up, it may build up in some places and not as much in others, and you could get something called inhomogeneous broadening. In that case, the peaks will broaden, and in fact, you could see, you know, when you try to charge correct, you may see things that are less than what they should be. We've all been down the hard road of learning these lessons. If it's semiconducting, then it's a little more complicated. You need to think about what's right. Look in the literature, people have gotten reasonable data in that case. If the sample's a film, I would adhere it to a sample stage using double-sided copper tape, for example. Make sure it has a low vapor pressure. If the sample's a powder, what we often do is take some indium foil, thin indium foil, is very soft, and put the powder down onto a flat piece of aluminum foil, Reynolds wrap. Put the powder down there and press the indium foil into the powder, and because the indium foil is soft, the powder usually adheres very well. That's a very good method. Is sputtering necessary? Well, do you really need to sputter? If you're trying to clean a sample, yes. But if you're analyzing a polymer or something that has an organic coating, you don't want to sputter it because you'll change the sample. Okay, whoops, sorry, I hope I didn't, okay. We're almost done here. Once the sample has been introduced into the analysis chamber, you need to make sure the vacuum is good. Now, be cautious because sometimes, I want to check the time here, I'm almost done. Sometimes the pressure could be 10 to the minus 9, 1 times 10 to the minus 9 torr or lower. And then you turn on the X-ray source and the pressure goes way up. And it's not always the X-rays, it's not the X-ray source itself, it's photon-stimulated desorption. X-rays hitting the sample and desorbing. So sometimes what happens is you need to make sure the sample had really been dried if possible. And sometimes it's just going to be the nature of the sample and you have to decide, am I going to take the risk with my machine and run it 1 times 10 to the minus 8, 2 times 10 to the minus 8 torr. I would not, unless you have one of those fancy near ambient X-ray sources, it is dangerous to start running XPS at pressures higher than a few times 10 to the minus 8 torr. Have we done it? Yes, but we try to avoid it, okay? Usually what you want to do is then perform, so if you do have high pressure, what will happen, it may not ruin your machine, but you can get micro arcing, which causes noise in the spectrum. The first thing you want to do is do what we call a survey, a wide range, maybe scan from 0 to 1200 electron volt binding energy. And you want to see what elements you have. Usually 100 EV or even 200 EV pass energy is okay. The higher the pass energy, the worse the resolution, but the greater the signal to noise. The reason then you might want to do carbon 1s and see how charged it is. If it's showing up instead of at 290 instead of 285 electron volts, then you may want to adjust the region scans so that you are more or less centering the photoelectron peak. Otherwise you're going to take spectra, you're going to go to write your paper and it's going to look weird where the action is at the one side of the spectrum or you may miss part of the peaks. An adequate number of scans needs to be performed. I have seen so many papers in the literature where people take a spectrum, then they start trying to peak fit, and they're peak fitting noise, and so we want to avoid that. Basically be aware of also the sensitivity factors. So when you go to quantify how much carbon, how much oxygen, how much aluminum is on the surface, what happens typically is you measure, the computer will do it, the area of the peak. But not all of those photoelectrons, well, the photoelectrons are being ejected with different probabilities. And there was a very famous paper by a scientist named Schofield. And the Schofield photoionization cross-sections have been theoretically calculated. Most instruments are using the Schofield factors. And so anyway, that's usually built into your machine along with the transmission function, which is something related to the probability of this transmission through the spectrometer. Then we're going to talk about peak fittings, and my colleagues are going to talk about that. And I guess that's kind of my part. I will be happy right now. I have more or less kept to the time. I think it was Yeah, good. Can I assume, would you like to ask any questions now, or I will stay, of course, for or would you rather wait till you see everything? Anyway, I hope that you learned something about how your photoelectron spectrometer works. So I'll turn this over. Any questions at this point?
I think it's good to ask questions for Jim now.
Okay.
So the slides here.
So I just want to ask how to measure. Okay, thank you. How to measure the total is energy resolution. I know about the energy resolution depend on so many parameters.
Yes,
Yeah,
very good question.
So should I have the basic as a measure to measure the.
Yes, this is a beautiful question. Thank you for that question.
The same sample, use the same parameter, and measure which peak. So we should.
So the question really is, how do you know the energy to do it? One way to do it is to put in a standard, like a gold sample or silver sample, and you would probably like to sputter it, and then to run that spectrum and measure the full width half max. The manufacturer of the machine, when you buy it, usually provides reference spectrum, and so you see, does your full width half maximum match that? The other way, which is a little more complicated, not much, is to measure the Fermi level of so that you can go down to 0 electron volts binding energy and look at the Fermi level and see basically how steep is that curve. Most people do what I suggested first. But there is literature and still, by the way, even though XPS and ESCA have been around so long, there's still debate about how to charge correct, and there's still papers published on how to measure resolution. I would do it personally with a silver or gold standard. Other questions? Yes.
So when person talk first. So one critical question. So slide 5 you mentioned if a more electronegative atom bound to carbon, the binding energy will shift to a higher direction.
Yes.
So my question would be, for example, if a palladium oxide and palladium chloride, they are both, how to say, 2+, we consider, will the binding energy different from the XPS measurement or not?
So they could be a little different, but the answer is I don't know.
Yeah.
I don't know the literature on palladium chloride. They could be very similar, and so I don't know the answer, but they won't necessarily be exactly the same. The question is palladium chloride versus palladium oxide. Both palladium would be in the +2 oxidation state in both cases. Just the oxidation state alone being the same will not mean they have the exact same binding energy. However, they may have a very similar binding energy.
But for example, if even the little bit different, will we still consider these two as same oxidation state?
Well, this is now where, okay, would they have the same oxidation state? You could have, you might not have palladium PD, you may not have palladium chloride, PdCl2, you could have PdCl, it might not be exactly 2 to 1. And so the answer is, I don't think, you can get information from XPS. If they are the same, it is an indication that they are the palladium is in a similar oxidation state. But there's also, you notice I mentioned something called final state effects. And so all of this is just an approximation that the final state is, the final state of the atom is staying the same. But it would be a good indication. In other words, in the end, what I would do if I were you with that kind of experiment, I would find literature and compare my spectrum, calibrate it, and charge correct it to the literature to answer that question.
Okay, so if I'm allowed to have a second.
Yeah, go ahead.
For example, if a palladium particle, I'm studying heterogeneous catalysts. If a palladium particle on support, so for example, alumina oxide. So if considering the particle center, the oxidation state will be obviously different compared to the interface, like the corner side, palladium bound to the support. But from the XPS, if you measure it, you will get the average result, or
Yeah.
you are able to distinguish between them.
Yeah, so we come now to one of the general limitations of XPS. It is a relatively low spatial resolution technique, and so you're going to get the average. You're going to get the average. It's just the way it is.
Yeah.
Other questions? Yes. Well, I see we have a couple. I'll go with you first, if you don't mind.
Thank you. That was a very useful talk.
I hope so.
And my question is not stupid. I'm quite new to XPS.
No such thing.
So you mentioned that we generally mention the X-ray source, but you also mentioned something about the pass energy.
Mm-hmm.
So where does that does that come automatically?
Yeah. So they're totally separate parameters. Energy of the
that
determines
part
the
I
energy. Yeah.
understand.
Okay.
The pass energy.
The pass energy is the energy that is being, basically the energy that is being, of photoelectrons that are being allowed to make it through the analyzer successfully. So the pass energy, you can control when you set up the experiment. Usually they can be, you can set it as small, typically as 1 or 2 electron volts, and as high as hundreds of electron volts. So they're totally, the photon energy is determined by which anodes you use. The pass energy is ultimately determined by the voltages that go on these 2 hemispheres. So in other words, the outer and inner hemisphere, the computer is setting high voltages on there. And so the pass energy is the energy that is being allowed to cleanly pass the photo to the detector from the, but there's this pre-retardation going on. Retardation helps the resolution, energy resolution of the experiment. If you don't pre-retard, you don't get very good energy resolution. And the other thing is, in fixed analyzer mode like this, all of the peaks will have the same energy resolution. But the answer to your question is the pass energy is related to what electrons are passing through the detector. And that has an important effect on the width of the peaks. So you would like to use, you don't want to use the smallest pass energy available. So what happens is, as pass energy goes down, energy resolution goes up. But at some point, going lower in pass energy doesn't help you anymore, because you're being limited by something like the photon, the X-ray source full width half max. So what you need to do is an experiment like this, if you're interested in getting it right, where it's very easy, you just run this spectrum, run the same spectrum at different pass energies and find out where does it stop getting narrow, because you don't want to run too low because you give up signal noise. Does that help?
Yeah, thank you. So,
You're welcome.
and now I understand what pass energy.
Yeah, it's very important.
Yeah. But for some of the, we don't have the facility, we not typically give our samples for measurements
Right.
elsewhere.
Yes.
And so then do we also
I would
ask
tell them, what I would recommend there, this is important. I see so many papers in the journal where people don't report pass energy. I would recommend that you tell the analyst to use pass energy, for example, of around 20 electron volts. My colleagues may comment and add to this, but 20 is usually a good number, for the region scan.
But
20
that's
EV.
useful for us
And-
because when we don't have
Yeah.
the luxury of
Yes,
asking
you don't have this, it's not easy. 20 EV will usually be very good, and you would like to have enough data points. So typically I run every 0.05 electron volts steps, because if you don't run enough and you try to peak fit, you get other problems. Okay? You're welcome. Other questions? Yes?
You mentioned that for different samples, conductive or insulator, you use different preparation methods. But when I get one sample, I don't know what is conductivity.
What kind of sample?
Special
Yeah.
powder.
Yeah, okay, it's a, what is the, do you mind that, tell me what the sample, what kind of material? It's like a metal oxide or something, or?
Sometimes the students told
Okay.
us that it's conductive, but
Well, I mean, usually what will happen is that if it's usually a metal oxide or something like that. I'm sure that's what you're dealing with these days, probably. So what will happen mainly is it will charge up, and it'll charge up, eventually reaches equilibrium. I mean, what you have to do is deal with it after the fact, and what you would like to do is pick something to charge correct to. Perhaps a carbon 1s, you would, if adventitious carbon is on there, you would shift all regions the same amount such that the biggest carbon peak is at around 285. However, if you have an element, let's say you're running zinc oxide, for example, and you know there's zinc oxide in there, it might be better to charge correct everything so that the zinc is in the known binding energy for zinc oxide. So long story short, you're going to have to charge correct. If you don't have the luxury of trying this experiment and this experiment, just give it to the analyst, you get the data, and then you charge correct it by picking something, and then you check, do things look reasonable and so forth. My colleagues might want to add to that. But the answer is you do what you can. Yeah. It's very common these days, and so what I do, we do this all the time. You know, you take the metal oxide powder and you run it, and then you charge correct. I mean, that's what's happening. Okay, other questions? Okay, in that case, I'll turn it over. Thank you very much.
Yeah, I think that was a very good introduction of a good start of the workshop. So I'm going to continue. Jim already said that XPS is very useful. It gives you some information that no other tool can give you. But he also warned you that it's a low resolution technique. So what we're interested in is identifying chemical species. And we identify them based on the chemical shift or the shift in binding energy that they have. Unfortunately, this shift is about the same size or same magnitude as the width of a typical XPS peak. So quite often you cannot directly identify the chemical species, and you need to do something what's called peak fitting. And peak fitting is you can quite easily do in the software. And this is not going to be a tutorial about a certain type of software. Everyone has their own preferences, and as long as you know what you're doing, the software shouldn't really matter. So this is really going to be about how to peak fit. So, and the title of my talk is XPS errors. That's a little bit too narrow, because I'm gonna definitely show quite a few errors, mistakes people make, because I think that's a useful way of learning. But I'm also going to explain a little bit, I'm going to delve a bit more into some aspects of photoemission, the physics behind it, because that's really important before you start peak fitting yourself, to make sure you start with good initial guesses. And then, so what I forgot to mention at the start of the workshop is that Jim is an editor at the Journal of Applied Surface Science, and Emile and I are managing editors. And a while ago, I did a small survey, and I looked at manuscripts submitted to this journal. And as for a surface science journal, not surprisingly, about 50% of the papers that were submitted to this journal had XPS data. Unfortunately, 87% of them had a problem. So if you think, oh boy, I made a mistake with my XPS fitting and it's published, well, there are many people out there who've probably done the same mistake. So don't feel too bad, but hopefully after this workshop, you know how to avoid any of these mistakes. And the biggest mistake is that people don't report what they're doing. And as Jim mentioned, quite a few of the experimental parameters, they determine your quality of your data and how your data looks like. And you need to report that so other people can assess the quality of your data and assess your analysis, because unfortunately, quite often the analysis is incorrect. Then technical issues with peak fitting are also too frequent. ambiguous presentation is probably the easiest to avoid, but quite often it's not really clear what the data shows or what the peak fitting shows. And then probably the worst category is you have some peak fits that simply violate physics, and that then basically you could have just as well not have included the XPS fitting. Probably would have been better. And this is, of course, not just this journal. I want to show you an example of a preprint. To be honest, I made this slide in November last year, so I'm not sure what the current status is. But this is a highly contentious field. It's high pressure superconductors, and this is not my field, so I can't really comment on whether these are superconductors or not. But someone pointed out that it contained XPS, so that's why I was interested. Oh, it contains XPS. Let's see what they report. And this is their experimental section of what they did in XPS. So it's basically 1, 2, 3 sentences. And what they report is the machine that they've used, the make and model of the spectrometer. That is really useful to report. They report the fitting software. I don't think that's too important, but it doesn't hurt to keep it in there. And then they, this is very important, they use what's called a surety background, and I will give examples of different backgrounds. I'll explain a little bit about the background of a surety background, but that's indeed very important to mention. And then the last thing they mentioned is the peak shape that they use. 80% Lorentzian, 20% Gaussian. If that doesn't make sense to you, then that's good, because I have a nice slide on that. So they've mentioned 4 things. Unfortunately, they left out what the X-ray energy is, which is very important if you want to distinguish between XPS and OJ peaks, as Jim mentioned. They didn't report where their source was had an acromy layer. Typically, most modern machines do. They didn't mention whether they use any charge reference, charge compensation. They don't mention how they referenced or calibrated their binding energy peak, and they didn't mention their pass energy. So if we now look at their data, so this is the first mistake they've made, not reporting what they've done. And this is the oxygen 1s that they published. So this is the oxygen spectrum. And there are actually quite a few things that are not great about this spectrum. First of all, if you look at this, if you look at the experimental data, so that's the black points here. You see it's a single peak. It's asymmetric, meaning that this side here on the right is narrower than the side on the left. So that's a clear indication that in this case there are probably multiple species. So I agree that they didn't fit this black peak here with one peak. But equally, I can't really see why they use 4 fits. In peak fitting, it's often you peak fit to test a certain physical model. And the more peak fits you have, the better your fit is going to be statistically. But it's not necessarily scientifically any meaningful. So it's often, if you start peak fitting, try the simplest model possible. So start with 1 peak. If you see, okay, with one peak I can't get a good fit, add a second one. And if you still can't get a good fit, then clearly your model is too simple and you need to extend on your model. But to just go for a rather a single peak with 4 peak fits, that's a bit problematic. And the second, it's also ambiguous what this legend means. I mean, yeah, sure, we all know these are oxygen 1s peaks, but what do they mean? Well, what is this? So I mean, now the combination between this is absolutely meaningless. A keen observer also sees that this background, this is probably, again, a surety background, that's what they mentioned, but it goes in the wrong direction. It goes down where it should go up. I'll explain the details a little bit later. So then they present this atomic model of their sample, and apparently it contains 4 different oxygen species, oxygen 4, 3, 2, 1. With a relative ratio of 1, 4, 7, 4. However, if you look at the peak intensities here, the areas of the fits, there is never a 1:4:7:4 ratio. So the model is not consistent with the peak fitting. So, and they also do some LED spectra where you can see here that it's not, the peak fit doesn't really describe their data here. Also here it overcuts their data. So there are quite a few things wrong with it. And now I want to take a step back and look at the fundamentals. So I'm going to talk, basically that's an extension of some of the slides Jim showed. So we're going to talk about spin orbit splitting, the origin of certain peak shapes that we observe in XPS, widths, why certain peaks are asymmetric and how you should fit those. We're going to talk about the backgrounds, this so-called Shirley background, but also others. I'm going to extend a little bit on the charging and the references, how to do that. And then we're going to talk about oxygen vacancies quickly. So spin orbit splitting is the first item. It's a well-known thing from physics. So it's a relativistic effect, meaning that, for example, if you start with an atom before you start ionizing it, you have 3 p orbitals, px, py, pz. They all have the same energy. But what happens now when you take one of these electrons out, you start to you have a core hole and a spin. That spin couples with this orbital, and in fact these 3 orbitals that had the same energy, they're now being split into one orbital with lower energy and 2 with higher energy. So the result is that in XPS, every orbital we measure, except for s orbitals never split. So if you see a nice single peak, that could be a sign that it's an s orbital. But otherwise, they come in pairs. So the p orbitals, they come in 2 pairs, and their relative, their labels is called p1/2, p3/2, and their ratio is 1:2. Same for your 5d orbitals, they're being split into 2 sets, 1/2, 1/3, so the relative ratio you measure is 2/3, and same for the f orbitals. The separation between these 2 components depends on the element and orbital. So, and this is a value you typically find in literature, and through your peak fitting, if you're going to decide to peak fit both spin orbital components together, then it's good to keep that just constant. So in the first estimate, don't make that a fixed fitting parameter, just keep that fixed. And also keep the area ratios fixed too. That's very important. So not the peak intensities between the 2, but the areas should be 1 to 2, 2 to 3, and so on. And this is an example. This is titanium 2p. So 2p, as I said before, is split into 2. This is the 2p 3/2, has an intensity of 2, and this 1/2 has an intensity of 1. And the area of this peak, so the area of this peak is half the area of this peak. If you're a keen observer, you notice that the peak intensities, they don't scale 1 to 2. I'll explain to that a little bit later. But the most important point here to take home is that this both this titanium peak and this titanium peak, they originate from the same initial state, the 2p orbitals of titanium, and therefore they contain the same chemical information. And it's also very important to, if you're going to fit, make sure you fit this peak. In this case, I fitted this peak here with two peaks, one for titanium 4+ and a small shoulder here for titanium 3+. So now it's also important that this other spin orbit component is fit with a 4+ and 3+. And also that the relative ratio of these fitted peaks are again 1 to 2. Now, if we're going to look at the shapes and widths of XPS peak, so for example, a carbon 1s electron has a binding energy of, let's say, 284. And now, can we measure this with absolute precision? And the answer, of course, is no, because there's a thing called lifetime broadening. So basically, it's from quantum mechanics, the Heisenberg uncertainty principle, that links the energy and the lifetime of the species. So the more we know about the lifetime, the less we know about the energy. And this means that for a given lifetime, we also always measure an uncertainty in energy. And this is a Lorentzian peak shape, this results. And a Lorentzian peak shape you can recognize by having a very wide base and a very narrow peak. You may very well never measure nice Lorentzian peak shapes in your spectrometer, because this is not the only broadening we observed in your experiment. Your source can add additional broadening, could be Lorentzian, could be otherwise, depends a little bit on the source. Your analyzer adds another uncertainty, which scales with the pass energy. So higher pass energy, more uncertainty about this binding energy, or broader peaks. Sample can be a bit homogeneous. You can maybe have several different states that are not completely similar. And most of these additional sources of uncertainty, they're Gaussian in nature. So a Gaussian peak is quite different from Lorentzian. The base is actually narrower, but the peak itself is wider. So in that sense, it's almost the opposite of the Lorentzian peak shape. So if we have a small pass energy, we limit the amount of additional broadening we get from the analyzer, and we can get a more Lorentzian shape. But it does depend a little bit on your source. But definitely, if you use larger pass energy, you get more Gaussian shaped peaks. The question now is, can we, this is a bit wordy and not very specific, can we do a little bit better? And so I don't want to scare you. This is all the mathematics I'm going to discuss. And I see that the sign didn't really come through. But in any case, what's happening here is this story here, this being more Lorentzian or more Gaussian. You can express that or you can calculate that mathematically by using a convolution. So it's blending one function with another. So we blend this Lorentzian curve, we blend that with a Gaussian. And this image more or less represents the effect. So we have this red curve, which could be a Lorentzian or any other function, and we have this blending function, this blue one, and the resulting convolution is the green, which is basically the overlap of the two. So if this blue square is not overlapping, the result is 0, but here it starts overlapping, we have full overlap, and we go down again. So this helped me understanding what a convolution is. You don't really have to understand too much more. One important thing is that peak fitting in literature is quite often called deconvolution or deconvoluting. But mathematically, a deconvolution is the inverse of this process. So peak fitting is not really, most often peak fitting is not really a deconvolution. So it's best not to call it that. And the resulting peak shape is this black one. It's called, it has a special name, it's a void function. So it's a convolution of Lorentzian with a Gaussian. And numerically, that was very difficult to calculate on computers. So we use approximations. For example, this Gaussian Lorentzian sum, which is Gaussian and Lorentzian added to each other, or this product. Computers these days, they can do convolutions quite easily, so there's no need to use these. But on the other side, their approximations are pretty good, and it's very unlikely that just using these will lead to any error in your interpretation. But the important is that whether you use this void, a product or sum function, now your peak shape and total width is given by a Gaussian width and a Lorentzian width. So basically, the total width of your peak depends on both, and the shape of your peak depends on the ratio between the two. So if you start peak fitting, you have to provide initial guesses. And Oh, sorry. This slide actually says something different. Yeah, the peak shape should be fairly similar for all peaks of your region, preferably also for your sample. So sometimes I see peak fits where they fit, for example, carbon 1s, and you see one very Lorentzian peak, and the other is very Gaussian. That's a sign that it's not really a good fit. So as I said before, the width of this Lorentzian depends on the lifetime of the excited species, and I've shown the titanium 2P before, and that's somewhat a classical example. I've said that the area ratio between this peak here and this peak here should be 2 to 1, but this one is much wider. If you look at the full width half max of this one is 1.3, and here it's almost double. That necessarily means that the intensity of this one is lower, because the area should still be half of this one. But it's much wider, so it's lower. And that is due to a lower lifetime of that species. So we have the photo emission of this 2P, and then we have an additional Auger process that's only possible for the 2p1 half, where this empty state here is filled with an electron from the 3/2. This excess kinetic energy is then transferred to a valence electron that's being excited. So that reduces the lifetime of this peak, hence it broadens this peak with respect to the 3/2 half. This is mostly significant for the 2p orbitals, and less so for the 3D and 4F peaks. So the Gaussian, and that was asked before also, the Gaussian depends on path energy, and how do we estimate the Gaussian width in a sample? Or as Jim explained, it's best to use a peak with known width. So the gold 4F and silver 3D are good examples, because it's easy to clean those materials, and people have measured them over and over again. So the width of these peaks, the Lorentzian width of these peaks are quite well known. So then you can use that to determine the Gaussian width that your experimental setup adds. So that's both your source and your analyzer. The alternative is to measure the Fermi level of your sample. That's handy in case if it's not your system, you don't know, or maybe you have forgotten this and you don't have access to the system anymore, then you could analyze the Fermi level. This does require that there is a Fermi level, so it needs to be conductive. And then the Fermi level is basically the highest energy, the highest filled orbital of your sample. And at 0 Kelvin, it's basically a step function, but at every temperature above 0 Kelvin, you get this smoothing of these sharp curves. This is described by Fermi-Dirac distribution, and you probably noted that your sample temperature, so you can calculate how this looks like. What we measure is again a Fermi-Dirac distribution convoluted with a Gaussian. So by fitting your valence band, your Fermi level with this function, you can, and if you specify the temperature, you can get the broadening of the experimental broadening of your setup. The peak shape is unfortunately not that easy, because quite often you encounter asymmetric peaks, and this is actually a pretty subtle asymmetry, but what we mean is this line here indicates the peak position, and you can see the asymmetry best if you look at the base of this peak. This distance is much shorter than this distance, and that's quite often, and it can originate in several different things. So to start identifying where this asymmetry is coming from, your first question is on which side is the asymmetry, and how much does this asymmetry extend? If it's only tenths of an EV or maybe a few EV, then the physical origin is probably different. So most most asymmetry comes from the fact that as the photoelectron is generated, or as it moves across the sample, it can excite different species, and it loses kinetic energy when it does so, and so it loses kinetic energy, and because we plot this in binding energy, this side is actually low kinetic energy side, so it ends up at this side of the peak. So another reason could be unresolved states. This is a graphite sample I measured. It's some funky plasma printed graphite. But what you can see here is that it's very asymmetric, and it extends for several V left of the peak energy. And so in this case, the best solution was to fit it with several peaks that are unresolved. So, for example, carbon-carbon, CH, CO, and double bond CO. One thing I should mention here is that the convention is to plot binding energy from high to low. Unfortunately, my users in this case didn't do that, so you will see that quite often, and can be a little bit confusing. So here they plotted from low binding energy to high, but so you basically have to flip this spectrum. In any case, if you've measured a spectrum and you're going to assign, you're going to say, well, I think I have carbon bound to oxygen or to other atom, it's very important to then also measure the oxygen one has and see if you can fit it with the same model. So, for example, here in this model, you see that there's more CO single bond oxygen than double bond. So if you're going to fit the oxygen, it's important that in your oxygen result you also find more single bond oxygen. So there needs to be internal consistency in your fitting. For some maybe a little bit rare cases, there could be vibrational excitation. This is a result of carbon monoxide adsorbed on rhodium, and here the photoelectron excites certain CO stretch vibration in the molecule, and that leads to these distinct loss features, these distinct peaks here. And if your resolution is high enough, you can see them actually more clearly as distinct peaks or shoulders. But if you work, so here I try to reproduce this artificially, so if your resolution is very high, you see distinct features. But if your resolution is lower, they blend into this general asymmetry. And the final origin for asymmetry is electron hole pair excitation. So if we look here at this is a calculated electronic band structure for a certain material. We have a valence band here. The pinkish states indicate where the electrons are, and at some point we have the Fermi level. It's the highest occupied orbital, and above which the states are empty. And what can happen now as the photoelectron is excited, it further excites electrons from here into the empty states. And because you have an almost unlimited amount of combinations you can make from starting to final point, you don't get specific loss feature, you just get a general broadening. And this is important for conductors. So oxides generally have very symmetric peaks. And it also depends on the density of state at both sides of your Fermi level. So if you have a lot of electrons here, if your Fermi level is in a highly occupied band, you see more asymmetry. So that's why if you measure gold for F, even though gold is a conductor, it's fairly symmetric, the peaks. And platinum is a very asymmetric peak. So here on the left you see a plot. These are all shifted such that they overlap. And you see that the gold 4F is much more symmetric than, for example, the platinum, this pink one here. So, but if you're going to fit platinum, you need to make sure you use asymmetric peaks. And you almost always need to use approximations because you don't know the electronic structure of your material. So you can use a very easy approximation that's called a Doniuk-Sunjak function, and that assumes that your electronic structure, the density of state is constant until forever. And that gives you reasonable good fits, but it's important to mention that this also is a little bit problematic in the sense that you can't integrate your signal anymore. Because if you integrate this function, it goes to infinity. There's another broadening called Mahan, which assumes that this density of states is linearly decreasing. It's not used a lot, it's more complicated, but it could be interesting. And if you really want to go fancy, you can try to calculate with DFT how your electronic structure looks like and derive a fitting function. We tried it here. I wouldn't necessarily recommend it, but you could. So most people either use Dunjik-Sonjek, and then you have this alpha parameter that determines how much asymmetry you have. And this function is plotted over here. So with alpha 0, this Dunjik-Sonjek function is equal to a Lorentzian function, and the more asymmetry you have, the higher your alpha value is, the more asymmetry you have. But as you may have noticed, that this is still Lorentzian, so this result is a Dunjik-Sonjek function. You still need to convolute with the Gaussian function. Here you see such an example. This is platinum, and it's a combination of different platinum oxides and metallic platinum. So I had to use a very asymmetric Dunjik-Sonjek function for the platinum, the metallic platinum, and the symmetric peaks for the metal oxide. And here you can see the problem with this Dunjik-Sonjek function is this doesn't go back to 0. It will stay flat forever. So you see, if you start integrating the green peak, you need to artificially decide when you stop integrating, which can be a little bit difficult. So there are people that have taken a different approach. So they didn't use any physical assumptions or predictions. They just used any empirical asymmetric function. Again, there's no physical basis for that, but it could lead to very, very good results. But you have to be careful that you do not influence the results with certain choices of functions or fitting parameters. And these are two examples of different groups who have proposed different functions to do just this. I highlighted a few times the difference in backgrounds. So the most simple background is just a linear function between 2 points A and B. It's not the best background, but it's the easiest background. And if your peak to background ratio is high enough, then to be honest, the choice of background doesn't really influence your results too much. The most widely used is a surety background, and I have a nice example here. It basically looks like a step function, and it's surely proposed, I think in 1970 already, that the reason why the XPS background is always higher at the left side is because the amount of background scales with the amount of inelastic scattered electrons. And what does it mean, inelastic scattered electrons? Those are electrons from this peak that have lost a certain amount of energy. Then they don't end up here in the peak anymore, they end up somewhere in the background because this is the low kinetic energy side. And surely now propose, well, the intensity of the background scales with the amount of photo-emitted peaks on the right side of a certain point. So here at the beginning, background is low because there's no emitted photoelectrons, but as soon as we start going into this peak here, the background rises because it scales with the intensity in the peak. A physical, more sound background is a Tugard, but it's rather complex. You often need to measure wider regions. And I want to emphasize this is actually an active field of research. So, but pragmatically, I would suggest using the surety background. But as this slide here shows, it is really important where you start and where you end. And if you use the surety for a doublet, it's also important that you get different results if you use 2 different sureties for every peak or 1 surety for the 2 of them. And there's no a priori way to say which is better, but in this case, you could check which is better just by integrating this peak here and this peak and see what the relative ratio is. See if that relative ratio is what you expect, is what it should be. And sometimes, that I showed in the beginning, this surely always needs, if you go from right to left, it should always go up. It should never go down. And sometimes it can actually happen if the background before the peak is actually sloping down, again, considering going from right to left, then if you start fitting a Shirley background, you see that the Shirley background will be inversed. In that case, you have to do two things. You first have to fit a linear function here, subtract that linear function to make sure that this pre-background is flat, and then you can fit a Shirley. Jim mentioned this already in his presentation in the question session, so I'm not going to say too much about this. If you have a conductor, it's fine. You don't have to worry, but most of you are not measuring conductors because oxide semiconductors, insulators, are sometimes more interesting. And you can mitigate charging. That allows you to actually measure the sample. You would do that by using a flood gun, which floods the sample with electrons and ions. If you don't have a flood gun, you can heat your sample. Heating is typically quite effective in reducing charging. Or sometimes you can add gas if you have one of these fancy ambient pressure XPS systems. That's fine for you to collect data, but it doesn't guarantee that it neutralizes all charging. So you still need to do some charge referencing. The most rigid way rigorous way is to add gold clusters and then measure the gold 4F and reference to that. No one does that because it's effectively too difficult. What everyone does is use a peak with known position. Quite often it's this adventitious carbon at 284 point something, and this point something is done deliberately because you find different values in different papers. It's practical, but it's limited at the same time. For example, you don't know that you have the same carbon species for every sample, so then it's difficult to find a constant species. Also, you're not guaranteed that your carbon is electrically connected with your sample, so it could charge differently. It could charge a little bit less or a little bit more. So if you then take the carbon as a fixed point, you translate that uncertainty in the peak position of your sample. However, sometimes you need to do something, so my practical advice, go ahead, use a carbon peak. First read this paper. This is from people who complain that this is terrible to do. So it's good to know their criticism. If you use a known peak, you need to report how you've calibrated for that, how you shifted your peaks. That's very often not done, and it's really important. But also present the spectrum of the element you're referencing to. For example, if you reference to carbon 1s, it's a good thing to, at least in the supporting information, show that carbon 1s. And then be mindful of the limitations. So don't report binding energies with 0.01 precision. That's great if you can do that, but it's probably meaningless. And be careful to interpret like very small shifts in binding energy. Because they could be an artifact of the calibration. Oxygen vacancies is something you often see in XPS because oxygen vacancies are important in many materials. So if you have an oxide that's treated a certain way, you typically find a peak and a shoulder or two peaks. And then they say one is lattice, one is the oxygen vacancies, but it's been recently questioned in literature how valid these assignments are because oxygen vacancies are typically not stable in air. So if you have oxygen vacancy in material, you take your material from the application, you bring it through air to the spectrometer, the vapor, the moisture in the air could have basically removed all these oxygen vacancies. So that's why it could be important to treat your sample in a certain way in the spectrometer, or make sure that you find some vacuum suitcase vacuum transfer from your application to the spectrometer to make sure that the oxygen vacancies, if they're present in your sample, are actually preserved in your spectrometer. Okay, I want to, now you're almost as experts as I am in XPS fitting, so we're going to look at a few more bad examples. So this again is poor fits, right? I mean, you don't have to fit. If you just want to show, I measured this sample because, and XPS shows it has iron, that's fine. You show the iron 2p. Don't start presenting this because the position here is meaningless. This is not a good fit. This wouldn't. They probably forgot to press the fit button here. Make sure your background don't overshoots the data by this much. Here, yeah, this is also not really good fitting. If your data is too noisy, so my background is synchrotron-based measurements. So users come to our beamline and they have a short amount to their experiment. So inherently they create noisy data. If their data looks too good, I tell them you're wasting time, move on to the next spectrum. But there is a point where your data is too noisy. Here in this nitrogen 1s spectrum, you can say, well, there's some nitrogen on the sample, fine, but don't fit this because the uncertainty in this peak position is huge. So, yeah, this is too much variation in peak width. So there's a peak here, a fit here, a fit here, there, but this is also a fit. So that's just way too wide. This is just background. Same for carbon 1s. There you quite often see large variations in peak width. So this is also peak, and that's too wide. And by now you also recognize that this peak has a really wide base, so this looks really Lorentzian, whereas this green one looks really Gaussian. That's a minor issue, but it's still not fantastic. Sometimes you have to be mindful of the resolution of your experiment. So in this case, this peak is way too narrow to be real. This is probably just a spike in the noise that they try to fit. Lithium is difficult. Cross-section of lithium is quite low, so you need to measure for long times. But yeah, this could be lithium, or this could be lithium, maybe this. So that doesn't say too much. There's a very narrow peak here. This is a really quite problematic fit in many aspects. Here the signal to noise is quite low, and it also violates this spin orbit splitting, where I said, well, you need to have a pair, and every pair of every part of the pair needs to be fitted with the same number. Again, this is pure noise, so that should never be fitted. Here is a metal oxide, but you see that it's a very asymmetric peak for the metal oxide, and by now you know that only conductors basically have very asymmetric peaks, but metal oxide should be fairly symmetric. This I showed at the beginning, too many peaks. This is also an interesting, even if you do everything correct, because other people make so many mistakes, you need to be careful how you report your own data. So here in black is the experimental data, and well, let's assume the fitting is perfect. You always need to show the sum of the individual peak fits to show that the total fit matches the experimental data. And here, only the experimental data is plotted and the individual peaks, but not the total fit. Sometimes they overlap. If they overlap, what you should do is plot the residual, which is the difference between the fit and your experimental data. For p orbitals, d orbitals, f orbitals, you should label every peak by its spin orbit labeling, and a chemical assignment, not just the chemical assignment or not just the orbital labeling. Often you have difficulties because certain peaks do overlap. Is antimony and oxygen overlap? So this is mostly oxygen. I mean, this here is antimony, oxygen, carbon, but it's not clear that they correctly identify this peak as oxygen 1s and not as an antimony 3D 5/2 peak. So you need to be very precise with your labeling. So this also is incorrect, and it's maybe a little bit more difficult to see. But whenever you see a 2-to-1 ratio, you need to be very careful. This is carbon 1s, so s orbital, so no spin orbit system. This is a 2-to-1 ratio, which is your first hint that it is actually spin orbit split 2p orbital. And this is actually potassium 2p and not no carbon species. I showed it before, so yeah, here they failed to recognize that. Here they fit the 2p 3/2 with 2 peaks, and here only with 1. That's also not correct. Use the same number for both. This is, yeah, you need to make sure that the relative ratio between the two is this ratio that you predict from physics. So for this 3D orbital, it should be 3/2. This one can never be more than this one. And here you see another problem with relative ratio. Here in this 1/2 region, it's almost a 1-to-1 ratio, where here you see that the ratio is 2-to-1 or 1-to-3 almost. So they need to be counted. So it's the ratio between the green and this gray fit here. This ratio should be equal here and there too. And then if you fit and you see it's not the case, then you need to fix this ratio in your fitting function so that it is the ratio you expect. And if you then find out it's not fitting properly, you may want to add additional peaks or do something else. This is probably the last thing I'm going to talk about, and unfortunately it's also the most difficult bit. It's some orbitals, some elements, they have open shell structures and difficult electronic configurations, maybe both before and after the photo emission. And pragmatically, you need to remember that if you fit one of these red elements, so it's mostly manganese, iron, cobalt, nickel, and cerium 3D is also another example, then you need to be very mindful and have a good look at literature. And one of the examples is manganese. So this is a pretty good reference here for manganese, and because you have so many, this is pure manganese oxide, manganese 2+, and you see that all of these peaks, they correspond to manganese 2+. So, but often almost all manganese literature you see that they fit a single peak per oxidation state, whereas the actual structure per oxidation state is already quite complex. And one way to resolve that is to measure reference samples. So measure your manganese-containing samples you're interested in, but also measure different pure manganese oxides. And instead of using synthetic peak shapes, you can use this entire curve shape to fit your data with. And you just use a linear combination of several of these curves to fit your data. Yeah, so be careful. Be careful fitting your own data. Be as careful as reading literature, because unfortunately you can find for every mistake there you will find several people who have made that mistake before you. So yeah, please reach out to me or to one of the other organizers if you have any questions or need help. This is a relatively recent, it's actually published now. So I think if you just search this title, you can easily find it. It's a pretty extensive review paper on all these errors. And with that, I would like to stop, I think. Are there any questions? Yes, please.
Is there another good way to fit the metals like copper or iron? Because these metals, the spectrum is very complicated, like the satellite is, and the different state have different satellite. So
You're talking about copper, right?
yeah, something like that.
Yeah, so for copper, the copper 2+ has this clear distinct satellite feature that you can easily recognize. The difference between copper, metallic copper and copper 1+ are more difficult. So what people tend to do is measure the Auger spectrum of copper at the same time, and then you can look at the difference between the Auger and binding energy peak. It's called the Auger parameter, and that could give you an indication which type of copper you have.
For example, for the pure metal copper and oxide copper, and is there any standard spectrum of this poor material?
Yeah, you'll find there is this a journal called Surface Science Spectra. It's published by the American Vacuum Society, and they publish lots of spectra for standard samples. So they have an entry for metallic copper, they have an entry for copper 1+ oxide, copper 2+ oxide. So you can have a look and see how the spectra look like. And then, as I said before, you can measure the Auger of copper. They're also distinctive for the different oxides. And of course, the oxygen 1s should also be different between the metallic copper and copper oxide.
And for the binding energy gap between the objects splitting, for example, the 2p 1/2 2 and the 2p 3/2.
Yeah.
Yeah. These two peaks, the gap between them is equal, but sometimes it changes.
Yeah, there's some empirical reports that for certain compounds it fluctuates a little bit. I think you should be fine if you start your fitting just using a constant, because the variation are quite small, I would say, with respect to your other parameters, your fitting parameters. So start off by keeping them constant and look them up on literature. A good website is the Thermo XPS website. They have a database of all the elements with the spin orbit, spin width. And I would keep it always fixed if I start fitting. And maybe if your other fitting parameters are very close to perfect, you can free that fitting parameter, see if it changes slightly.
Yes. Thank you.
Hi, Phil Davis from Cardiff. Nice talk, Matthijs. I want to make a comment rather than a question. Two comments. The first is, as I think you were saying, everybody needs to do their homework when they've got spectra to fit, to interpret. There's a lot of stuff out there, and it's quite easy to hone in on the standards, the ones that people have done. That's one thing. And the other is a plea to everybody in this room. You're all going to be sent papers to a referee, and many of them will have XPS, often in the subsidiary information. Look at the XPS. It's up to all of us who know about XPS to make sure that the fittings are done well. I can't count how many papers I've seen which are really good papers where the XPS fitting has been disgraceful. And unless everybody checks it and points out that it's wrong, we'll never get this corrected.
Yeah, I agree. Thanks. Yeah, by signing up for this workshop, you also sign a contract that you're now XPS ambassadors for life. So it's now a shared responsibility. Are there any other questions or comments?
Thanks for the talk. I was just wondering, is it okay to use carbon to cut elaborate on the data for coverage materials?
I would say yes, that's fine, as long as you report what you do and be careful about the limitations. So make sure that if you have several samples and the carbon 1s spectra look completely different, then the answer is probably no. The carbon 1s is maybe not a good reference. But if you have a set of samples and your carbon 1s spectra look pretty similar in a way that you can identify a certain peak in the carbon 1s, I think it's fine. It's probably the best you can do. But then in your experimental section, report that you've used that method to calibrate the data, report the position of what you think is a known position of that peak, and probably also show the carbon 1s spectra. Okay, then I think it's time for Emile.
So, good afternoon everyone. So I am Emile A. So maybe you can go to the next presentation. Yeah. Yes. Okay, so just a question before I will start. Who works with coating? Just please raise your hand. Okay, some of them with powder or single crystal. Okay, so what kind of sample do you have? Like, if it's not powder. Okay, anyway, so today I will talk about so XPS the profile and also the cleaning, which is quite an important step. And I will just start with a quotation that from a paper that can summarize the two previous presentations, but also my presentation. It is better that to do XPS measurement to have, and also to have some specific question in mind before you do the experiment. So just a very short introduction of myself. So I have a background of material science from Europe, and since 2016 I moved to Belgium and I started to learn XPS with that guy, Jean-Jacques Pirot. So if you work with polymeric materials, you have probably heard about this guy. As Matthijs, I'm also a managing editor at Applied Surface Science. So if you have any question about all the editorial process, feel free to contact us. Okay, so this will be the table of content of my presentation. First of all, we will talk about the cleaning. Okay, why we have to clean, how we can clean the sample, and when we have to clean the sample. And then we will move to the XPS the profile. Okay, so how to do it, what are the methodology, the limitation, and try to avoid to have like wrong interpretation of your data. Okay, so let's start with the cleaning. So first of all, why do we have to clean? So I think that now you know that because we just probe the very top surface of materials. Okay, so this is an example of a survey spectra of tantalum oxide just as received and after cleaning. What you can see here is that just as received you have a lot of carbon, a lot of oxygen, and you may see some tantalum which is just buried below this contamination layer, and you can even see some silicon. But as soon as you, and of course here the ratio between tantalum and oxygen is not good, what you should have. But as soon as you clean it, okay, this is a good cleaning because you do not see any carbon and no silicon. So basically the contamination comes from the dust, okay, because there is a lot of dust in the environment, but also some biofilm handling, the handling process, because you have some sodium chloride on your skin, so especially if you eat some Belgian French fries before doing experiment. You can also have some oxidation or hydroxide formation due to the storage, if it's a humid storage and so on, and the exposure to the atmosphere. For instance, if you play with fluorine-based materials, fluorine can absorb at almost any surface. And sometimes in some labs it's even forbidden to use fluorine-based material within the XPS. So what we generally see is carbon and oxygen contamination, but also silicon, which can come from PDMS, so it's polymer. It's a polymer that you can find in all these plastic bags or sometimes some of the gloves, and also metal oxide formation, native oxide and so on. That's why you just need to clean them. Otherwise, you will have a scabrous interpretation of your result. Okay, so just what you have to know is even if you put the sample, if you store the sample in a vacuum or even in ultra-high vacuum, you may still observe contamination. Okay, so just to give you an example, this is gold sample stored for 20, I think it was like 24 hours in air, high vacuum and ultra-high vacuum. So you know that gold is not a reactive metal, but you still see some contamination, carbon and oxygen, except if you use really ultra-high vacuum. And some materials depends of the affinity with oxygen and the environment. But for instance, zirconium may form like carbohydrate materials, and so those metals are highly reactive to the environment. So you may observe also different contamination depending the element that you want to use. Okay. Okay, just some example why we have to clean it and what kind of spectra you will obtain. So first of all, you will always observe contamination whatever your materials, can be minerals, can be coatings. What you will see, okay, so, oops, sorry. So this is the evolution of the signal as a function of the cleaning. So here, for instance, in this calcium-based oxide, what you will see is you just, after the cleaning, you will remove this CC bond. On this titanium nitride coating, what you will see is that you will remove the oxygen from this coating. And on that one, you have like over-stoichiometric oxide on the top surface, and then you will move to the oxynitride composition within the film. Okay, so the first step is try to limit this contamination. Okay, so how to do that? So first, try to avoid the long duration between the synthesis and the analysis. Always wear gloves, okay, and please use polyethylene or free nitrile gloves. Okay, the other one can contain PDMS. Also work with some instances that are dedicated to the XPS, not for the synthesis, for instance. And try to avoid the use of plastic bag and so on. You can use, for instance, aluminum foil to pack your samples. This is better. It is also better to do the XPS before the SEM, okay? Because then SEM you can have like carbon contamination due to some vacuum difference and oil during pumping and so on. And sometimes you also have to deposit gold during just before the SEM imaging, so this is better to do the XPS before. And if you have to cut your sample, please do it into a very clean area, otherwise you may observe huge contamination. Okay, so there are different methods then to clean the sample. The best one is to do in situ cleaning, okay? Like for instance, in situ polishing or in situ annealing. Unfortunately, those methodology, you need to have a very specific setup. So most of the XPS spectrometers, you will not have such setups. That's why you can do in situ cleaning by two other methods that I will present today: cluster cleaning and ion cleaning. Okay. So the cluster cleaning, I think this is probably the best one. Okay, but you have to have a special source, a cluster source for that. Ion cleaning, it works, but you have to be really careful when you will use it, and this will be the main topic of today. So just to give you some example of different sources, okay, so I am not working for Thermo Fisher or other companies, it's just example. I know that there are other sources, but just to give you an example. So this is the argon plus, okay, one of the ions that you can use, and those are the cluster. Okay, so you can use like C60 plus cluster or argon-based cluster. So those one, the argon-based cluster are the more recent cluster source. So the ion cleaning, we'll call it the rough one, okay, because here you have just a very quite high energy from 0.5 to 4 keV, depends on the different spectrometers. You can choose the current, you can choose the raster size. I will explain a bit later what is the raster size and why it is important. And you can have a sputtering rate, so it means that you will remove the materials from 0.1 to 1.5 nanometers per second. Okay, so quite heavy. But it induces a lot of damage, okay, like reduction or preferential sputtering. So then, that white cluster is probably much better, and you have basically two sources of cluster. The first one is the C60 cluster. We'll call it the gentle one, okay, that was initially used for SIMS application. I think that the first one was probably proposed by Ionoptica. So here, the sputtering rate is about 2.4 nanometers per minute, okay, here on the silicon oxide sample with this raster size at this voltage. And you do not have too much subsurface damage with that one. And then the most recent one, the let's say gas cluster source, which can be made, so you can have like cluster from argon, and then this is really versatile because you can choose the size of the cluster and so the energy. And when I'm talking about the size, you can go from cluster, very small cluster, like 75, up to 2,000 cluster. And you can also generally tune the energy between 2 to 8 keV. And this works really well on a wide range of materials, and you have very low damaging of your surface. Okay, so now, how we can clean it? So this is the basic methodology. So first, you choose an area of your sample, which is out of the interest area, but these places need to have quite similar composition. Okay, just to try to find the best methodology. So then you record the contaminant, like for instance the carbon and the oxygen, but also the element of interest. Then you apply a set of parameters, so for instance, the duration of the cleaning, the energy, the size of its cluster, and then you just repeat the steps up to make the contaminant disappear. Okay, so just to see when those contaminants will disappear. Then you have to check also for some damage. Okay, for instance, if you see some artifact like reduction or modification of the surface, like changing the composition and so on. And as soon as this methodology is ready, then you can move to the good place and to do the analysis of the sample, but before for sure applying this the cleaning methodology. Okay, there is no standard procedures about time, duration, number of steps, and so on. So you have to find yours because each sample will have a different cleaning procedures. I can give you some number, for instance. This is an example of titanium nitride coating that has been analyzed on a thermo-K alpha spectrometers. What I generally do, because we have two of those XPS, one is with a cluster, so cluster you can work between, let's say, 30 to 300 seconds, okay? But if I have to use like monoatomic source, argon plus, I will just sputter clean a very short time of maybe 10 to 60 seconds, okay? At quite low energy to try to limit damage in the surface. Okay, so here it's an example of a profile, okay, on a PMMA coating. So this is a depth profile. I will talk about depth profile a bit later. But what you can see here is those are some artifacts, and just to, so this is a slice of the profile. I will explain a bit later that one. But just to show to you here, if I have to clean this sample, and it would be acceptable to clean the sample with argon plus, but just with a very short time, okay? Because as soon as you increase the time of erosion, then you will observe a huge deviation of the composition. Okay, this is normally the real composition, and this is the measured one. Okay, so you have to be sure that you will not induce too much damage. However, if you use here a cluster source, carbon-based cluster source, then it is safer to just maybe sputter a longer time. Okay, you can maybe sputter like 2 minutes, it still will, yeah, the sample will be okay after that. Okay, so then let's make a decision tree, okay, to know if you have to clean the sample, and so to see basically when it is necessary to clean the sample. So, do I have to clean my sample? The answer is no. If you do just in situ deposition and then you just move, like Matthijs said, with a vacuum sweep case or transfer sweep case to the XPS, and if you just do the analysis, it should be okay. You do not really need to clean the sample. Okay, so, but imagine that you have to clean it and you have a cluster source. So then, quite safe. So you are safe, you can find the good parameters, try to be as gentle as possible when you clean the sample, and always be critical on your data, because this is probably the most important. So then, if you do not have any cluster source, but you have an ion gun source, okay, this is feasible, but this is a bit tricky. Okay, so again, be gentle as possible, and you will have artifacts. Okay, this is definitely, you will observe some artifacts such as some chemical reduction, preferential sputtering, ion beam mixing, and so on. So so don't discuss the chemical shift, basically. You can discuss about the composition, but then because the ion gun will induce too much damage, so you should not discuss the chemical shift of your sample. So then, if you do not have any cluster source or anomalous, I think it's time to write a proposal to find an equipment, or maybe to find another group with a good equipment with such a source. Okay, so let's move to the depth profiling. Okay, this is basically the methodology of depth profiling. In a sense, this is cleaning, but just repeat several times the cleaning. Okay, this is basically what we do when we do depth profiling. So what you do is you first apply the X-ray, collect the signal, and then you just switch off the X-ray or blank the X-ray, and then you go for the ion beam. Okay, you just sputter the surface. So basically, you dig a hole into your sample, and then you repeat the X-ray. Okay, and again, so X-ray, ion gun, X-ray, ion gun, and you will go through the surface. Okay. So it is an example of one of the recipes that I did on one of my samples. The sample was titanium oxide deposited onto titanium adhesive layer, and this was deposited on stainless steel. So here we can use a flood gun. Okay, the flood gun is the charge compensation gun, so the one that Matthijs and Jim mentioned, to avoid charge effect, at least to limit charge effect during the analysis. Then there is the step to switch on the X-ray. So here I used a spot size of 250 micrometers. You can see that it's quite recent sample. Then here I did an initial survey spectra because it's always good to check okay, if I am on the proper surface and so on. And then this is the depth profile step. Okay, so I choose the element of interest, but also the element of the substrate. Do not forget it. For instance, if you do a depth profiling and you want to cross the whole surface of the wall coating, for instance, you also have to record the substrate element. And then you just loop those steps. Okay? And don't forget to switch off both the ion gun and the fluid gun and the X-ray gun at the end of the experiment. Okay? So, just one word. Generally, for depth profile, depending on the spectrometers, there are two modes of analysis: the scan mode and the snap mode. So, scan mode is the one that James has presented before. So, you scan all the energy of the electrons, and the snap one is basically you collect the whole energy range of the electrons, and this one is much faster. Just to give you an example, a scan on just for one high resolution spectra will be about maybe 10 seconds, something like that. You have to repeat at least several times, but you can do 10 snap within a second. So this one is much faster, especially when you have to repeat all those steps to get a full profile. Okay, well, the quality of the images, I think, is a problem. Okay, and this is really strange because normally you should not see such a very poor quality. I don't know why. Okay, so basically what you can see here is one slice of the profile. Okay, so so here you should see normally like, so this is the titanium, this is the oxygen, and this is the iron. Okay, and for instance at step 100 second. Okay, so then you will have plenty of those slices, and then you will observe the evolution of the signal as a function of the etching time, therefore as a function of the thickness. Okay. Here what you can see is that we have the titanium, okay, and the oxygen for the titanium oxide, and then behind that there is a substrate which is made of stainless steel. That's why we have some iron. Okay, so then we have to reconstruct the composition profile from all those high resolution spectra. They are not so well high resolution because this is a snap mode, so the resolution is a bit lower. Okay, so for that, what we have to do is to integrate those peaks. Okay, and you know why they are so poor quality. But then you can convert the area to the concentration using the Schofield factor. Okay, the one that Matthijs presented. So here what you have is here the oxygen, the titanium, and the iron in green, with a titanium adhesive layer. And here what you can see also that we have some, so the blue one is a carbon 1s, we have contamination at the interface between the coating and the substrate. Okay, so, but you have to be careful when you do these steps, okay, so the reconstruction of the profile from the data, because depending on how you choose the background, depending on how you choose the limit of the integration, and how you choose the signal-to-noise ratio, you may observe different composition, okay, so you know that it is titanium oxide, so you should have one titanium for 2 oxygen, so therefore you have to be careful when you reconstruct the profile, okay. So just for instance, for background here, you may observe some discrepancy depending if you take a linear one and so on. Okay. Okay. So just an example of the effect of the signal-to-noise ratio. Okay. So basically, what is this parameter? You just say, is it really a peak or is it just noise? Okay. So you have a parameter to adjust. If you choose, if you don't apply any ratio, so let's say that you just disable the ratio, then what you will see is that you have, so in red, I think this is carbon, you will see carbon in the coating, carbon in the substrate, because every single noise peak, let's say like call them like this, will be counted as a real element, which is a nonsense, okay? So you have to remove all those peaks. So that's why you have to apply a signal-to-noise ratio. If you choose a too small ratio, therefore all those noisy peaks will still be counted into the profile. But then if you choose a very high one, okay, then you will miss the small real peak. So here basically what you can see is that the titanium one is not counted into the profile. Okay, the titanium is a purple. So you have to be careful when you choose this ratio. The ratio about 1, from 0.8 to 1.5 is a good compromise. Okay, so as I showed to you, you can reconstruct the profile from the wall signal, okay, but you can also do fitting. Okay, it's really a mess at the quality. I don't know, I probably got the transformation for when I load the presentation. But so here what you can see is that we have 2 contribution in the titanium, okay, and what you can do is you just, so here in red and green, this is the 2 contribution of the titanium oxide. It is legit, but just be careful that the ion beam will induce damage. Okay, so it means that the discussion of the evolution of this ratio is probably not meaningful, okay, because you may induce a lot of damage with the ion. Okay, so now let's talk about the limitation, about, for instance, the thickness and the duration of analysis. So if you want to analyze a very thin surface, I would suggest to use angular resolve XPS, or the one that James presented. Then, if you want to work with quite thin coating, between 10 to 100 nanometers of thin analysis of the surface, it's okay to use a cluster or a small cluster. Okay. Then moving with bigger thickness up to 1 micron, you can use the Argon one. Okay, it will take about 1 to 3 hours of analysis per sample. It is okay to go at higher depth, okay, so higher thickness, but it takes time. Then if you want to move to like thicker analysis, it's better to use another techniques like glow discharge optical emission spectroscopy or SEM cross-section coupled with EDS and EDS depth profile and so on. Okay. Talking about how, so what will be the number of steps and which time step do we have to use? Just remind that you will probe between 5 to 10 nanometers. So there is no sense to use a step size below that one, okay? Because otherwise, at each step you will scan also the result from the previous step. That's why at least 8 nanometers. But to be honest, I think it's better to use between 20 or 40 nanometers of analysis, and to have in order to have a good profile, it is nice to have at least 50 points. It means like at least 50 steps of analysis. So typically, here you will have an analysis of maybe 1 or 2 hours, depending on the number of elements that you will analyze. Okay, so other limitation, the raster size and the spot size. So the spot size is the size of the X-ray spot, and the raster size is the size of the erosion gap. Okay. Generally, you have the raster size is generally much bigger than the spot size. Why? It's because this is 2 gun, and you have to be sure that the 2 gun are really well aligned. Okay, otherwise you will dig a hole here and you will analyze there. So there is no sense to do that. By default, is about with the raster size is the spot size multiplied by 4 or 5. Okay, so if you decrease the raster size, you will increase the erosion rate, okay, because you concentrate more energy on the limited area. It can be nice in some cases, but then you may also observe some problem. Why? It's because the bottom of the crater will not be flat, okay? So it means that if you choose a quite large raster size, you will have, let's say, quite flat crater. But then imagine that you reduce the red one, okay? It means that you will have a very, let's say, curvy crater. And then, for instance, if this is a multi-layer sample, you will have a very poor depth resolution. Because at a certain time, you will analyze the black one and the white one in the same time. Okay, so that's why it's important to have quite a large raster size. And I have some photographs after that. So just to have a good compromise in terms of erosion rates and quality of the analysis, you can go for between 200 and 300 micrometer of spot size, and you multiply by 5 the raster size. This is quite a good compromise. So just to give you an example of the analysis, so this is a SEM cross-section of one of our coating. So this is a multi-layer. You can see that it is really well, beautiful stack with an adhesive layer here and the silicon substrate. This is the crater after erosion for the top seams. This is the crater for XPS analysis and these spectrometers, and this is another spectrometer. So you see that depending on the spectrometers, the different crater can be really, really different. So now let's talk about the results. So this is the top seams results, very beautiful profile, which is in well agreement with the observation. And if you do, for instance, EDS line, you will observe exactly the same one. And this is XPS depth profile. Okay, so what you can see is that as soon as we enter into the coating, we just like mix everything. Okay, so, and then this is not diffusion. Okay, this is just an artifact. I will explain it more later. So about the effect of the argon energy. Okay, so this is an example of so the depth profiling of this sample. So from here to here, we reduce the energy, but we also reduce the number of snap in the collection of the signal. So what you can see is that even at from 2 to 1 K, we still have a huge ion beam mixing phenomena. And if you reduce more the energy, you will have quite nice profile, but you still have the ion beam mixing. Don't look at the edge time because it was just a very long experiment just on purpose, but you should not have an experiment with such time. Definitely too long. Okay, so yeah, this is the conclusion. So here you do not have to say in the paper, okay, I have diffusion in my coating. No, no, no. This is here just artifact because you mix everything with your ion, okay, reaching the surface. Okay, other problematic interpretation of your data, the effect of the roughness. Okay, so if you put a coating or an oxide or anything on a surface, and if the surface is flat, really flat, like silicone, mirror polished silicone substrate, you will have a very sharp interface. Okay, so this, for example, yttrium stabilized zirconia that has been deposited on silicone wafer. So silicone wafer is really, really flat. Okay, so here, when you do the profile, you will have a very sharp interface. If you deposit the same coating on an alloy, you will have a much wider interface. Okay, because the alloy is really rough. Okay, and then you will probe at a certain time. You will probe the substrate and the coating in the same time. Okay, so basically here this is not interdiffusion and so on. No, it's just an artifact because of the roughness. Okay, be careful because the roughness can also be induced by the beam. Okay, so this is a bit tricky when you discuss. You have to have all these possible problematic interpretation in mind when you discuss the data. Okay, what about sample with cracks or with hole? For instance, same coating that I showed to you before, but after mechanical deformation. Okay, so this is a top view, SEM top view. But you can see here that we can see the substrate through in those cracks. Okay, it means that when you will do the XPS depth profile, you will see the substrate. Okay, so it means that here you will have iron and chromium in the coating. Okay, so here the blue curve. This is the iron that comes from the substrate. Okay, this is not migration of the iron into the coating. No, it's just because you see the iron through by doing the analysis. Okay. By the way, just to give you an example here, we use this amount of iron to relate into the level of cracks in the coating. Because if you have more cracks and more holes, then you will see more iron in the coating. And another example of damages that can be induced is so ion beam reduction. Okay, so here is an example of MOS2 coatings, molybdenum disulfide. So molybdenum disulfide, you should have 1/3 of molybdenum and 2/3 of sulfur. But if you do depth profile of a monocrystal of that materials, you will observe variation of the composition of the function of the etching time. Why? It's because you have preferential sputtering. The sputtering yield of the sulfur and the molybdenum are different, and therefore they are sputtered differently, and then you will have a deviation of the composition. Let's talk about reduction. We can talk, for instance, about vanadium oxide. I know there are some experts about vanadium oxide in the room. So if you take a monocrystal of V2O5 and then you do XPS analysis with depth profiling, so this will be the signal. So that one is the signal of oxygen and this is the signal of vanadium. Okay, and you will start with vanadium +5, and as soon as you go through the single crystal, you will observe new peak. Okay, with V4+, even V2+, and even metallic contribution V0. Okay, so that you can see if you sputter for longer time. Okay, so basically here there is no, you still have a very homogeneous sample, but again you induce a reduction of your surface due to the argon-based, so the argon bombardment. Okay, so this will be basically the end of my presentation. Just to tell you that there are different other methods to do the profile. So Jim mentioned angle resolve XPS, which is non-destructive. Okay, this is really nice and really adapted for very thin surface. And just also to mention that this is still a hot topic. For instance, one of the recent papers has been published in Applied Surface Science about the femto laser ablation combined with XPS to do the depth profiling. So basically here what you do is you change the cluster or the monoatomic source by a laser, and the laser will ablate the surface, and then you do analysis and so on. So they claim that they have really good resolution with a very limited amount of artifacting in the coating. Okay, so this will be my take-home message. So please always be careful when you discuss your data. Always take a step back, okay? Because you may have plenty of artifacts, and please always keep in mind all these artifacts when you discuss the data. And to be honest, I think it is always good to combine your XPS analysis with other methodologies, such as ILS or energy electron loss spectroscopy or RAM. Okay, we often see some paper with just TEM and then XPS, but yeah, to discuss about all the oxidation state and so on, this is better to combine the XPS with other analysis. Okay, so I will stop there. So thank you very much for your attention, and just also would like to thank all my colleagues from my previous groups for all the useful information. Thank you very much. Yeah, and if you want some, useful literatures, and I think that there is a paper of Matthijs, the one that you mentioned also, in those reference. So if you have any questions, feel free to ask. There was one there.
For the depth profile, we always do sample cycles or cleaning. Yeah. And for example, for sample with different thin film materials, different with one layer, top layer, and some layer, something like that. And how to translate the cycles to the depth?
This is really a good question. Imagine that you have nitride, oxide, nitride coating, okay, a stack with different coating. The etching rate will be different for the nitride and the oxide. Okay, so there is no direct, if it's 100 seconds of titanium nitride and 100 seconds of oxygen, of oxide, sorry, it might not be the same thickness, okay, because the sputtering yield and so on is different. What you have to do is to calibrate, or at least to measure the etching rates on separate materials. Okay, so the best one is for instance, to combine SEM pictures, cross-section pictures with the XPS profile. Probably is the easiest way. Other question?
Emile, I just have a quick question. If you use, I've never used a cluster gun to clean. With the C60, do you have to worry about implantation, or is the energy just so low?
Yes, you have to. You have to be careful to not use too high energy, otherwise you may also have implantation. This is also true for argon. Okay, if you do, for instance, the profile, you will see some argon in the coating. So C60, to be honest, now we see mainly the argon-based cluster, and those are really good because you limit the ion beam implantation and so on.
Thank you very much.
Other question? So if not, I think that you are now all experts.
Are there any other questions for
any of the speakers?
I just would like to add one thing, especially so as an author, when you refer to paper about XPS, please always go for surface journal, okay, like Surface Science Spectra or Surface Science. Those papers you will find much better reference than, for instance, catalytic journal and so on. I think that you have to choose the journal when you refer to the papers.
Are there any final questions? If not, I would like to thank my co-organizer, and I would like to thank you for your attention.